Okay, then we continue with more containers, in this case coherences for the container model of type theory, and our speaker is Stefania Damato. So please go ahead.
Thanks. First of all, I'd like to thank the organizers for organizing this event and having me here. So today I'm going to talk about some joint work that I'm doing with my supervisor, Torsten, who spoke just before me, and luckily he introduced containers, so hopefully you're prepped for my talk. So I want to start off with a motivation, why we want to construct a container model of type theory. And kind of how Torsten hinted at it, we're interested in the semantics of inductive types. And specifically, we're interested in giving categorical semantics for inductive types and quotient inductive types using containers. So containers have been used already to give semantics for strictly positive inductive types and inductive families, and we want to extend this framework to inductive types and quotient inductive types, with the hope of this hopefully aiding us to give semantics for higher inductive types. And so here I gave an example of a quotient inductive type, and this is the simplified intrinsic syntax of type theory. And so you can think of this as kind of an idealized Agda. We can extend this to give the whole syntax of type theory. But the point is that we have two sorts. We have a set con, and we have a family tie over con. So these are the contexts. You can think of them as the contexts. And these are the types over the contexts. And then we have these two types. And then this type is inductive because there's a lot of dependency here. So for example, in a constructor for con, I'm referring to this constructor sigma, which isn't declared until here. And then the quotient part of this is the fact that we have an equality constructor. So these are implicitly truncated as sets as well. So these aren't very high inductive types. So this is an example of a quotient inductive type. And in the literature already, we already know how to represent such types as the initial object in a certain category of algebras. And the way we construct this category of algebras is by first expressing the sorts and then adding the constructors one at a time. And the way we represent the constructors is by using functors. So constructors are expressed via argument and target functors. So for example, if I want to represent this constructor here, which was, if I go back, it was the second constructor here. So I'm assuming that I've already added to my category of algebras the sort con, the sort tie, and the constructor empty. And then I'm going to express this constructor using two functors, L and R. And L, you can think of it as like the left part of the constructor, which is the gamma and the A, so like the arguments. And then R is going to be the target, so con in this case, so the right-hand side. And the types of these aren't super important. The idea here is just that the left-hand side, given like a representation of the sort con and a representation of the sort tie and a representation of the empty context, I'm going to say that the left-hand side is just a context and a type over that context, which represents this gamma and this A. So this is like an encoding of this part. And then for the right-hand side, I'm going to take the representation of con, tie, and the empty context, as well as whatever the left-hand side did with that input. So that's why this goes from the category of elements of L to set. So so R takes also gamma and A and just returns C because it only returns a con. But you can think that in a more general case, this, for example, for a family, this can depend on these things and so on. But this is just a basic example. And the point here is that we conjecture that this framework, if we restrict the definitions of these functors to container functors, then we'll only be able to represent strictly positive types, and that's our goal. So our conjecture, which is like the kind of the big picture of our project is that restricting ourselves to container functors ensures we can only construct strictly positive QIITs. And as a prerequisite to this approach, we need a general way to express type contexts as containers. That is, we need a container model of type theory. So we kind of want a general way to express these constructors, that is, these functors, as containers. And so that's where the container model of type theory comes in. So the container model was outlined in an abstract by Torsten and by Ambrosch Kaposi in Types, and I'm going to go through the outline of the model. If you already know about the pre-sheaf model of type theory, you can think of the container model as a restriction of the pre-sheaf model, where we don't consider pre-sheaves, but we consider endo-functors on set that are container functors. So, so this is represented as a category with families. So contexts are going to be set containers. So the first definition that Torsten gave in his talk. So it's going to be a set of shapes and then a family of positions over those shapes, which we denote by this triangle here. And so these things, as Torsten said, have an extension functor of this type. So it's an endo-functor on set. Substitutions are container morphisms, so there are going to be morphisms between these things which correspond to natural transformations between container functors. The empty context is going to be the container whose shapes are, its shapes are the unit type, and it has no positions. Then we have to define types. So types in context gamma, so I'm thinking of gamma as a set container as defined here. They are generalized containers, so this is something that Torsten didn't cover. It's a different type of container. But the point is that, so we still have a set of shapes, but now the positions don't go into set anymore. They go into this category of elements over gamma, where gamma is a set container. So now types are these things, so generalized containers, and they also have an associated functor of this type. And the reason why we need to introduce this generalization to containers is because if we go back here, the containers that exist in the literature so far don't really cover these types of functors. So we needed a generalization. Terms are fairly straightforward. So terms of type A in context gamma, they're dependent natural transformations from the functor, the gamma functor to the A functor. So we use this end notation. And then lastly, context extension is given by this container here. So it's the shapes of A and the positions of A at the component X, because now PA has multiple components. And yeah, probably the trickiest part of this model is defining type substitution, which I'll get to in a second. But I want to first compare it to the pre-sheaf model, which is what I was saying before. So if you look at how we construct the pre-sheaf model versus the container model, you can see the similarities. So one thing I want to point out is that in the container model, the contexts aren't explicitly functors from set to set. They are set containers, like here, but they have an associated functor of this type. So this is how the pre-sheaf model and the container model relate to each other. So, or you can see that they're closely related. So yes, in this case, substitutions are container morphisms, which we said correspond to natural transformations on container functors, so similar to here. You can see that the types are very similar, the terms are very similar, and also the context extension. So this is, you can see the container model as an extension of the pre-sheaf model in this sense. So there is, in their abstract, Torsten and Ambrosch mentioned some issues with their model in the absence of UIP. So we're working in type theory, and because we're interested in higher inductive types, we don't want to assume UIP. So we don't want to assume UIP in our meta theory. So the first issue that arises if we don't assume UIP, and this is an issue that if we don't assume UIP in our meta theory also arises in, for example, the pre-sheaf model or the groupoid model, is that the collection of types is no longer a homotopy set, but it's a groupoid. So our tie functor doesn't go into set now, but into groupoids, because the way I defined types was types over a context gamma are generalized containers, and the collection of that is a groupoid. And so now, additional coherence laws need to be checked. So we need to check this law, which is associativity, and we need to check that tie preserves associativity and left and right identity laws, which are things that if tie went into set, we wouldn't have to check because they would hold automatically. So first of all, we have this issue. And the second issue comes up more specifically to our model. The way we define type substitution, so A substituted by gamma, we define it as a container whose shape is a pullback and whose position is a push-out. So it's this container here. And the problem with this, as we know, is that pullbacks and push-outs are unique only up to isomorphism. And we want the functoriality laws for tie to hold up to equality. But this, we don't get this because we use pullbacks and push-outs here. So yeah, the problem here is that functor laws do not hold strictly. So okay, how do we deal with these issues? So there's two routes that we can take to deal with these issues. So the first option we have is to stick with Debier's original definition of a CWF. So we stick with that and we try to make our model fit into this definition. And so basically we need to strictify our model, or we need to try to make everything into a homotopy set somehow. So that is the first option. The second option is maybe a slightly more principled way, and it's to view the model as a higher CWF, as suggested by Krauss and Yamura. And so basically, this is kind of the approach of, okay, maybe the original definition of a CWF is the wrong one, so to say, because we should allow types, for example, to be groupoids and higher types. And in this case, we would have to prove some extra coherence laws. I mean, in our case, we don't have to prove a lot more because we're not going too much. We're not going that much higher. But the drawback of this is that, as far as we're aware, we don't know how to interpret the syntax of type theory in this setting. So we don't know how to view the initial CWF as a higher CWF. So this is the drawback of this route, is that, yes, we agree that it is a more principled approach, but it also has a drawback. So basically, we do both. So we consider both options. So on this side, we took the container model as I showed it in a previous slide, and we proved the extra coherence laws, and they hold. It's fine, and they hold pretty straightforwardly from the properties of pullback and push-out. But we also have to assume univalence in this case for this to go through. So in the other case, we try to strictify our model by using a few well-known techniques. And so now I'm going to talk about the strictification techniques that we use to make our model fit into the set definition, the original definition of a CWF. So now we're going to look at the strictification of our model. So the first very well-known hack we can do is to use an inductive recursive universe. So we have a set U, which we can think of as like a type of codes. And then we have EL or L, which is like a decoding function. So U holds codes for my types, and then L decodes them into the actual types. So for example, contexts in the actual model, in the original model, were set containers, but now we say that contexts are codes for set containers. So again, we have a shape and a position, but now instead of set, we have U. So this ensures that we're not going above set. And then for types, so this solves the first issue that I showed in the previous slide. Now for types, we need to strictify. So one thing that we looked at, so if we go here, is how to strictify this pullback and push out construction. And we came up with a way of strictifying this by using indexed versus fibered notation. I think we were using the indexed, but if we use the fiber notation, this takes care of this, but we weren't sure how to strictify the push-out side of things. So what we do instead is we say that types in a context gamma, so we do what we had before. So we had generalized containers. Now we have codes for generalized containers to account for this change. So we have a shape and a position, and this corresponds to a generalized container. However, we also add a substitution. So this type is in context delta, and then we add a substitution into delta from some context gamma. And the idea here is also known as a left splitting technique, which basically it delays substitution as much as we can. So we only perform substitution when we need to do it. So you can think of this as kind of like the type B substituted by delta. So we're always kind of carrying this delta around. And the advantage of this, so how this solves the second problem, is that now type substitution can be very easily defined as, so if you think of this type here as B substituted by delta, we can define type substitution as, so you keep the same generalized container, but instead of delta, now you have delta composed with gamma. So you keep this and you change this. And so now if you try to prove the functor laws, they hold immediately. So now functor laws will hold strictly. So yeah, so with these two techniques, so the collection of types is now an H set, thanks to this, and functor laws hold strictly, and thanks to our new definition of types and type substitution. And so now I want to wrap up by giving you the kind of status of things where we've gotten to so far. So we worked out the details of the higher container model. So so Ambrosch and Torsten gave an outline of this model and an incomplete ACTA formalization. And we worked out the details, we proved the extra coherence laws, and so now we have a clear picture of what this is. We're currently finalizing the details of the strictified container model. So as I said, we tried a few things, especially with type substitution. And now we're working on this. We're at the final stages, so this should all work out. Another thing that we're doing is looking at constructing pi types, sigma types, and the universe in both versions, and this will probably, or we're looking at doing it in the same way that it's done for pre-sheaf models, but we still need to check that everything works out. And we also started a formalization of the higher, so of this one, container model in cubical AGDA. So this is, yes, this varies slightly from the formalization given here because we're using cubical AGDA. And yes, it remains to be seen whether this will be finished because it's very technical. But at least we have a framework for this project. So that's everything I wanted to say. Thank you for listening.
Questions?
So what syntactic results can you validate in this model? Like you said semantics for hits, I think?
What do you mean by syntactic results? Exactly.
For instance, does MLTT interpret in that model?
So yeah, I mean, we're trying to construct. I'm not sure if I understand the question, but we're trying to construct pi types and sigma types and universes. So yeah, I'm not sure if I understand the question.
Eventually, you want to add hits to the syntax of this type theory, right?
We don't want to add hits to the syntax. So the kind of the motivation. So I go back. So the motivation is that we want categorical semantics for hits. So I'm not really looking at the syntax of hits. I'm looking at the semantics of hits. And so a prerequisite to looking at the semantics is constructing this container model. So I'm not looking at adding hits to this model. This is just a prerequisite to looking for semantics for QIITs and hopefully eventually hits.
Okay, thanks.
I was wondering whether you know the dialectica model of Martin-Love type theory, and whether you, like, I have the impression it's also based on polynomial, and so I would like to understand whether there was a connection with this model.
I've heard of this, and I think I skimmed through it, but I don't remember the details, so maybe we can discuss this later. But yeah, I would be interested in looking at that. Thanks. Yeah. Yeah.
Yes, so this is Tamara von Glenn's model is different to ours. It's sort of it's a bit sort of simply typed where we have dependent types. So it's not really a subcategory of the pre-sheaf model. So yeah.
But is this what you're referring to by the dialectica model, or?
Yeah. Yes, there's one by yes, but yeah, I mean I haven't compared all of them, but Tamara's model is different to ours. Yeah.
The definition.
At some point, it's when you show this. At some point, it's sort of simply typed. It doesn't. Okay, I don't know exactly. Yeah, so a while ago I looked at this, but it's not a submodel of the pre-sheaf model.
Okay. I believe that like the types are defined differently in that they don't depend on the positions, something like that.
Okay.
Yeah, there's
Okay. You also had a question? No. Oh, okay. Then we'll return to the other side of the room.
Thank you. So one thing that's interesting with Tamara von Glenn's model is that it refutes function extensionality. What do you know what's happening in your model?
We haven't looked at this yet. So yeah, I'm aware of this. And yeah, actually maybe I should have added it in the, well, I guess like future work, which is I'm interested in looking at this. Yeah, but I haven't started. But we still have to check this.
Okay, any other questions, comments? No? Okay, then let's thank Stefania again.